this over there.
Hello, my name is Hugh Mcbroom, and this will be my XSAC on blacksmithing and iron metallurgy through the histories. Well, first off, what is blacksmithing? A blacksmith is a metalsmith who creates objects from wrought iron or steel by forging the metal with tools such as hammers and tongs. And basically, we hit really hot things to make shapes and tools and whatnot. Could you please change that? I'm just going to go. Because the field of iron metallurgy and blacksmithing is extremely vast, and I could cover an entire course on the subject, I'll briefly run down on several aspects that are reasonably related to blacksmithing itself and can't just be skimmed by. Okay, next slide, sorry. Next slide. Oh, shit. I apologise for that. I have not slept in over a day. All night is wonderful. Okay, the first step is, of course, the ore to iron. Iron oxide to reduced iron. There are two generalized methods in doing this process. One is the indirect reduction, and then there is the direct reduction. Indirect method involves like modern blast furnace and whatnot, and as its name implies, requires an extra step before it's fully reduced into the material you want. But direct reduction, however, is a process in which the metal is not fully melted. It's not melted at all. It's directly, the oxides in it are directly burnt away as it being a solid. And it's a direct path to reducing the iron ore to iron. This is far more relevant to the coming lecture slides, as the other process is more modern. So there are three basic kinds of iron alloys that are used. You have your wrought irons, your steels, and your cast iron. The wrought iron is the byproduct of the direct reduction method and is what's been used through blacksmiths for most of human history. Steel, as everyone knows, is like a modern construction material and whatnot. It's like extremely strong. And then you have cast iron, which is an extremely brittle material but has a lower melting point, so it can be cast into shapes. Another word for this is pig iron. Now, the difference between these three alloys is purely the carbon content. The carbon inside the alloys increases strength while decreasing ductility. But a byproduct of this is it makes it more brittle. Now, when something is really brittle, it can't really take a shock. It will fracture and catastrophically fail, which is not really good for something that needs to hold an edge or a hammer or something of that nature. So wrought iron, which is the complete opposite to cast iron, it has extremely low quantities of carbon in it. It's very ductile, easy to work with, and thus soft, and can be made to hammer things and whatnot. Steel is the region in between. It's just got a mid-range of carbon, so it's not extremely brittle and it's not extremely ductile, and because of that, it's got the best of both worlds. Okay, now that's out of the way, let's beat our way through history. Throughout history, the levels of iron working have varied across the world. For instance, well, the first civilization to really enter the Iron Age were the Mesopotamians. And they were full swing by the 900 BC. And then there are other civilizations, and the method they were using to create this iron and whatnot, normally wrought iron, is the bloomery method. The bloomery method is the process that uses direct reduction. Now, however, in this case, as I was saying, some areas develop different technologies at different times. China being a major exception to that, where it's pretty much developed a blast furnace instead of the bloomery process. It started making cast irons 2,000 years before it came to Europe. So I can't really go into detail about China because I'd be missing out on 2,000 years of history. So I'm going to leave them alone. I can't really touch on them because they skipped 2,000 years of metallurgy and just advanced quite a bit. Because the same process they were using in 300 and 200 BC did not reach Europe until the 14 and 1500s. A long time. But the process used in Europe and the Arabian nations and whatnot during that period, the several thousand years before the blast furnace took over, used something called a bloomery. Now, a bloomery is a reasonably low temperature furnace. It doesn't actually melt the iron. It just heats the iron or the iron ore to high temperatures with coal or charcoal. What the charcoal does is then decomposes to carbon monoxide. This carbon monoxide will then absorb the oxygen atoms inside the iron oxide and reduce it down to iron metal. This iron metal collects with a whole bunch of slag at the very bottom of the bloomery down here. They're called a bloom, this large chunk of sponge-like iron because it has large amounts of slag and whatnot around it, forms at the bottom. And this is, next slide, sorry. This is an example of a very, very large bloom, and this is basically where the job of a medieval blacksmith began. Because the first thing you have to do with a bloom is beat it to perfection, basically. They are filled with slag, which is an imperfection and greatly reduces the strength of the wrought iron, wrought iron is the product of this process. Very low carbon content, very ductile. The way they remove the slag impurities is hammering it constantly, back and forth. They literally beat the crap out of it until the slag clings off. It's an awesome way to do it, and I've worked on a very small plume myself, nowhere near the size of that massive thing. I'd be afraid to see how big the bloomery was. But with iron and steel working, you're limited in temperature to most forges throughout medieval history. They couldn't bring up the required temperatures to weld pieces of metal together. This meant that the size of the bloomery created was the maximum amount of material that could be used for a piece, like a sword or a plough or nails or chainmail or anything like that. You couldn't have anything of a greater mass than the size of your plumes. For many hundreds of years, most blooms were small and hand-powered, so they could only have a couple of kilograms. But later on, as horsepower and water power took over, bloomeries got up to 300 kilograms in size before the blast furnace took over, and that was big enough to make virtually anything. Next slide. Okay, now I'll go through the smithy itself. The smithy is a blacksmith's workspace. We'll work our way around the tools and the smith itself. The forge, of course, is a basic aspect of any smithy. You can't forge without a forge. It is the essential tool for heating up the metal. It's essentially just a large charcoal pit with an air vent in the bottom where you have bellows or some type of forced air supply into it. The greater air supply going into the forge creates greater temperatures, and thus you can work larger and larger pieces and whatnot inside the furnace, and then get up to like welding and whatnot, which is an incredibly difficult process to do. The temperature of forges were generally looked at by eye. A good blacksmith will be able to tell exactly the temperature of his forge and how his metals will heat up in it by the colour of the flames. Generally, the maximum temperature you'll be wanting is a white hot flame inside it. This is hot enough to fusion weld, and any hotter than that you'll ruin the metal. Next slide. Hammers and tongs. Well, I'm just going to say, because a smith makes his own tools and he makes them to whatever task he's doing, there's an endless variety of hammers and tongs. There's literally thousands of types, so I'm just purely going to say, and be safe in saying this, hammers hit things, tongs hold things, and that's what they do. You have other more designated tools, such as hole punches and whatnot, but the two biggest ones are just tongs and hammers. Okay, the anvil. Such a beauty. Them curves, it's amazing. It's the second most important thing of a smithy. Once you have the forge, you have to have something to hit the metal on to forge. But there is aspects of what a good anvil make. For one, an anvil has to not dent or something when you're hitting on it, which means the surface has to be extremely hard. But as we were talking about before, anything that's like really strong and hard is very brittle. And the worst possible thing would happen if your anvil shattered into a million pieces when you hit it, because you would also shatter with it. Sharp, very fast moving metal. So what they do is they get wrought iron, a very soft stuff that can handle shocks and absorb it all, and they make that the body of the anvil, and they fusion weld a very thin piece of very high carbon metal alloy onto the top. So it's very, very hard surface, but underneath it will be able to absorb the shock, and that's what makes a good anvil. Such beauty. And well, commonly blacksmiths made household objects and farm tools, basically, like almost all the time. That's their major jobs, where like as a farrier you'd be making horseshoes, and well, by the way, feel free to ask questions at any point if I skim something that you're interested in. And farm equipment like scythes and plows, and general farming equipment and kitchenware and whatnot. More rarely is like the swordsmithing and armor smithing, but as noted before, you can see direct correlation in the development of arms and armor to the size of plumeries. Because if your plume is only a kilogram, you can only have a small piece of plate. So they tended to make lots of chainmail and scale mail and things like that that don't require a single large piece of metal, because it's far easier to make. Later on, when there are larger plumeries, this wasn't so much of an issue, and they could make very large plate bodies, and it became a common thing. Yeah, okay. Okay, now we'll get into some techniques behind blacksmithing. But before we go into this, I put this picture here just because there was no other room in the oncoming slides for it. This diagram here is the temperatures related to colour of a piece of metal you're working with. Generally, well, I'll go into more about this later, but the critical temperature of an alloy is in the medium red range. It's 700 to 800 degrees. At this point, it's called the forging temperature, where the metal becomes highly ductile. Doesn't continually forms grain boundaries, something I won't really go into detail with because it's a complex issue and not for this lecture. But the colour scales go from a faint straw colour once it's been polished. You have to polish the steel to be able to see these colours here, and that's used in tempering to fine tune it in a heat treating process we'll talk later. But basically the main working range in colour is this red region here, and to fusion weld, which is welding the pieces together, you have to get up to bright yellow and white colours, which is extremely hot. Okay.
How do you stand near something that hot?
Gloves and whatnot, and face shield. Okay, now some of the common techniques used by blacksmiths to work iron are, of course, forging. That's like, you're not blacksmithing if you're not forging. But behind the forging process, there are 5 basic techniques. This includes drawing, upsetting, punching, and shrinking.
What's upsetting?
I will go into detail on these processes in the coming slides. I'm just mentioning them all now. You've also got welding, which is an advanced technique I can't do yet. It's quite hard, and generally for large pieces it requires more than 3 hands. And heat treating as well, which changes the properties of the alloys without changing their composition. They remain the same concentration of carbon to iron in the total material, it's just their internal structures vary. And processes behind this heat treating include hardening, annealing, tempering, and case hardening. Okay, continue on. Forging. Let's get more in detail of this. Just a quick modern look of what modern forging looks like. That is a shaft for a power plant. They are forging it into the right crystalline structure to be put into a forge. It's a massive scale, and it's pretty much done with machines for that type of stuff nowadays. And this is more like the blacksmithing that I'm describing.
Is that guy doing that with his bare hands?
Yeah, yeah.
That is not sensible.
It's not that bad. It's, he's, at the moment, looks like he's making a gun barrel. At the moment, he has this sheet of steel, reasonably thick, or whatever the alloy is, and he's got it up to fusion temperature, like the welding temperature. See how it's white hot there? That's the temperature you need to be able to weld a piece together. And what he's doing is he's hammering it around a cold tube, and he basically fusion welds it into a barrel, and then that's how gun barrels used to be made, basically, from forge. Now, I'll go into more detail behind the forging methods. Drawing, in drawing, the piece is heated to a bright red, which is the forging heat, and which is also known as the critical temperature. That one is important, and I'll come back to it. And hit repeatedly with a flat hammer on one side. Basically, you keep hitting it, it gets flatter and flatter and flatter, and gets wider and whatnot. You're basically like turning the plate, something like that. But you can hit in the direction and make it longer and whatnot, and you draw it out. You make it thinner and longer. Bending, as the name implies, is heating it up at a certain point and bending it. Normally you can do this either with hands with a long piece, or with tongs, or you could put it in a vise or something like that. Or if it's a really big piece, you could hit it on the anvil for a little bit to bend it into shape. Upsetting. This is one most people don't hear of that often, and it's not a very common one either. Upsetting is the process of thickening a material by decreasing its length and whatnot. The most common application is when you want to like thicken the end of a piece of rod to make a tool or whatnot. You essentially heat up the one end and tap it from the top, and it basically thickens the bottom of it. But this is not commonly done. Punching is basically punching holes and shapes into materials. You get special tools here that sit in the anvils and whatnot, and it's essentially like either a round or flat chisel used for cutting or something like that, and you just put it on the anvil and hit it with your hammer down, and it cuts the piece of metal when it's at a hot working temperature. Now shrinking is something I know very little about. I've never seen it done, but it's essentially does the same thing as upsetting, but it uses a bowl-shaped type thing that causes rippling and thickening. I really don't know how it works, and I've never seen it done, and I know a lot of blacksmiths. Okay, continue on.
It is the black magic, we understand.
Yes. Rare black magic. Welding. Okay, now there's pretty much only one process behind welding, but there are steps to it. And the first step is cleaning. Lots and lots and lots and lots of cleaning. If you don't scrub the surfaces of your two metals you want to fuse together to virgin metal, and it's not absolutely clean of impurities, the weld might not stick, and it might be a bad weld. So once it's been cleaned, it's put into the furnace and heated up. After this, a material called flux is put on. Flux basically just stops an oxide layer building up on the metal. It keeps it virgin, and then they're held together and beat together. That's how we get things done in blacksmithing. We beat shit up.
Sounds like a therapeutic job.
Yeah, it is. It's so great. It's how I get over uni stress. Continue on. Okay, and now the cool stuff, I reckon, or the hot stuff, whatever you want to call it. This is heat treatments.
How did you feel bad?
Before I go into heat treatments, though, I have to mention the TTT diagram, which stands for Time Temperature Transformation Diagram. Basically, this is a fancy thing of saying that alloys of iron have different phases, and I'll explain that in a minute. But these phases have different properties, and when you sit a piece of material at a different temperature on this graph and hold it at a certain amount of time, the composition of the internals of the material change depending on this graph. So I know it's not really readable, but up here is called coarse pearlite, and here's fine pearlite, down here is bainite, and down here is martensite. Over here you have something called austenite, which is involved in that critical temperature stuff and is unstable at low temperatures. It gets turned into this stuff below the forging temperature. Continue on. And back to those phases, there's three important ones, and they're not solids, gases, and liquids. Although solid gases and liquids are also phases in the exact same term, these materials are just a different kind of phase. They're all solid, but they're just a different crystalline structure inside the material. Now, these include martensite, bainite, and pearlite. Well, they're the three important ones anyway, for once the metal is cooled. And the key aspect about all this is, like, the iron alloy, all of the alloys contain the same amount of carbon and the same amount of iron, but they're not always evenly distributed. What happens is the carbon chemically bonds to some of the iron and then forms a material that precipitates out of the actual solution and as the rest solidifies. And this causes interesting structures. The material that it precipitates out as is called cementite. It's basically iron carbide, extremely tough material, and acts to strengthen the material, basically. More of these really fine cementite structures you have, stronger the material will be, but also more brittle, because it's more of this brittle structure. And basically, perlite and bainite are almost essentially the same thing. Perlite just has a very even size distribution between the cementite and austenite remaining, and it ends up looking like a zebra's ass. That's the shape that it produces. The black stuff and the white stuff are the two different kinds of material. And this is caused by a long delay in the TTT diagram. It's held at a high temperature for a long period of time. This means there are very large crystals inside of it, such as this, and that means it's more ductile and more easily worked. Now, bainite, on the other hand, is essentially the same thing, but on a much smaller and finer scale. Right here we have a small bainite crystal around austenite, and it's made up of extremely fine layers of cementite, which are these bands here. They're little bands of cementite, and one of these is essentially the same size as those entire structures there. And this causes bainite to be more brittle, but also stronger and tougher, and it will hold an edge better. Now, martensite, however, is something completely different. Martensite occurs when austenite, the material that all of these are created from at the high temperature, is rapidly cooled or quenched down before it can be turned into perlite or bainite or whatnot. It will form a solid that's super saturated in carbon, which is extremely stressed. It has lots of internal stresses in it, and it does not like its shape. It's extremely brittle and extremely hard. So continue on, but that you quenching is the key term there for that. And there's 4 kinds of heat treatments though, which essentially just decrease or increase the hardness, which in turn decreases or increases brittleness or ductility, depending on what you want. Generally, brittleness is bad because it fractures, and a fracture means it will catastrophically fail. Do you have a question? Sorry, it just looked like you were testing. Never mind. Okay. I don't have the 4th one there. Sorry. I lost it. Okay, the 4 heat treatments include annealing, hardening, tempering, and case hardening. Annealing, though, is where the material is brought up to above the critical temperature. That temperature returns into austenite. At this point, it's stable as austenite at that temperature, and then it's let cool extremely slowly. This turns the material into purely coarse perlite. That means it's very large crystals of perlite, and it's extremely soft and brittle, and ductile, not brittle, compared to something that's martensitic. So basically annealing softens it. That's what it does. It softens the materials and allows you to fine-tune how soft it is. Now, hardening is the complete opposite to that. It's where you take it above the forging temperature and rapidly cool it as fast as you can to turn it all into martensite. And this produces the hardest alloy for that composition you possibly can, but it's also very brittle. Now, tempering is something interesting because you don't, by the way, that's quenching. It's just throwing something in a bucket of water. But you can change the medium it's quenched in. Like if you quench it in oil, it's the rate that it decreases in temperature is lower, so it can form different compositions of bainite and perlite and whatnot. Now tempering is, I think I might have it on the next slide, but before I do that, this is just a quick tempering scale, because when a piece of metal is going to be tempered, it is first grinded back and polished, and when it's put over a flame, various colours will appear depending on its temperature, which corresponds here, where quenched temperature is almost white, and 730 degrees Fahrenheit is a deep blue going on grey. And essentially fine-tuning that means you can, say, stick the tip of a knife into a flame and heat it up quite a lot, and it will go blue while the rest of the blade is still brown, and doing that basically lowers internal stress. Heating a metal that's stressed out will allow it to release that stress, and it will become softer as well. Like, all metals will contain some stress, but allowing it to cool at high temperatures decreases that stress. So doing that, if you shove a knife into a fire part way, and you can have a gradient of heat traveling in it, and then quench it, you can get different hardness levels inside a single piece of material. Like, you can have a very hard edge of the blade, but the back be nice and soft to be able to handle blows and whatnot. Okay, now the decline of the blacksmith directly correlates to the introduction of the blast furnace and cast irons and whatnot, and the machine tools. But that doesn't mean blacksmithing's gone away. It's just been mechanized. Nowadays, blacksmithing is performed on machinery, and it's called hot working instead. It's you have rolling processes where you work sheet metal over rolls at high temperatures. You can create many different structures and whatnot, but it's no longer called blacksmithing. And anyone can do this. I do it as a hobby. If you stuff up, the great thing is you can always start again. You can always bring it back up to that austenite level, which takes it back to the raw point, and you can always work from there again. It's an awesome hobby for cold weather, guys. You sit next to a really hot fire for a couple of hours and you make shiny, cool things. It's awesome for Canberra. You should do it. And it doesn't actually require much strength, just precision. Where you hit the metal and how you hit it has to be very precise as you go through. And that purely comes with experience, and it doesn't really require that much force, because if you have the right temperatures, it's like butter. Well, not quite, but it does bend to your will. But yeah, you can do like awesome shit. You can make awesome things. I've seen a guy made a really cool dragon out of pieces. You can make decorations, art and whatnot, or functional things like knives for the kitchen, or swords if you really want to get into swordsmithing. Pain, trust me. And if you're interested in it at all, talk to me, because I'm part of a blacksmithing group and we would love to have you. Okay, there we go. Any questions?
Well, first I think round of applause.
How much does it cost to do blacksmithing stuff?
How much does it cost for a bit of metal at Bunnings?
Do you have to pay for the forge time though?
No, we're just, like, we're not really in association, we're just a whole bunch of people who use the forge out in Murray Embankment. It's quite, the forge we have at the moment is quite far out. It's on the edge of Murray Embankment. But I'm in the process of making my own small forge, which will be here in Canberra, and you'll all be welcome to work on it, because more the merrier.
You should set it up here. Right here.
Not in this room though.
No.
Blacksmithing is very loud.
Yeah.
It is extremely loud, and I've made sure already by my neighbours that they'll be fine with it. Yes?
I want to make guitar strings out of tungsten. Have you ever worked with tungsten?
No, and I don't intend to. It's a pain to work with.
Yeah, so I've heard.
It's extremely brittle, it's like all the extremes of a material, and I would not want to work with it.
Is it also pretty dense?
Yes.
Yeah, no. On a side note as well, the term blacksmithing comes from the fact that when you work iron, it's black. And there's also something called whitesmithing, which is the profession of a tinsmith. You have a tinsmith that works tin alloys and whatnot into shapes and whatnot, and he's called a whitesmith, while a blacksmith commonly works on irons and steels because the metal is black when it's coming out of the forge and before it's been grinded back.
Nowadays, what's commonly commissioned, or if anything is commissioned?
I'm part of a medieval society, so commonly handmade knives, daggers, swords, chainmail. Such pain.
I can see there's a lot of pain in chainmail. Care to explain that?
Okay, well there's lots of ways to make chainmail. Most people tend to make it with riveting that they can do in their own time. Then people want to get forge welded chainmail, which means heating up. Forge welding, like anything to do with forging, requires precision and timing because you only have a short period of time from it being hot to being cold, so you have to be quick. And it's particularly with fusion welding, where temperatures drop extremely quickly, and you can sometimes only have a few seconds to work with the material before it's too cold to work with. Now, imagine doing that with thousands and thousands and thousands of tiny pieces of ringed metal that you have to hit together at fusion temperatures over and over again. And if you get the temperature slightly wrong, you burn, like you set the metal on fire. Like at fusion temperatures, the metal is white because the surface of the metal is actually becoming liquid. That's how the two combine. It's two liquid layers combining together. Now, this means that the carbon is really, in the alloy, is really exposed to oxygen at that point. And at any elevated temperatures, even above a few degrees, will make the steel catch fire. It's a pretty sight, but it literally destroys the piece, and you would have to, I would not, you can't work with the metal anymore. You've destroyed its alloy composition and it's junk. And now imagine doing that with thousands and thousands of tiny metal rings, hitting them constantly, and they're nail. That's pain.
Okay, yeah.
Yeah. But then we also get things like spits and fire pits and fire stokers, decorative pieces, things to put around people's houses, all that type of stuff. But the most common thing is feasting gear for festivals. Everyone wants knives and forks and whatnot for a festival that looks medieval.
Is there actually much structural difference between a decent rivet joint and the welding?
Depends on how the rivet joint was made, because there is such thing as rivet welding. But yes, there is significant differences. Because think of the difference between a mechanical clamp holding things together and it physically being joined together as metal. Like, one can be broken with time and hit or off or something like that, when the other is literally welded together. You won't be getting them apart. Any other questions? And please, yes, go.
Okay, wait, so you know with the plunging where you put it into water?
Yes,
and
that's called quenching.
Quenching.
Yep.
Okay. And if you put it into oil, that
it slows the rate. Basically, they're called quenching mediums.
Yeah.
And there's many things, like you can quench in sand,
yeah,
which basically decreases the temperature extremely slowly, and you can almost say it's annealing at that point because it's going very slow and makes a very soft material.
Yeah.
Well,
if you plunge it in water,
could you go back to the very beginning
Yep.
of heat treatments with that TTT diagram?
Oh, wait.
This one, yes?
Yeah.
This basically describes how any heat treatments work. This
so you do have a phase diagram.
This is a TTT diagram, not a phase
Similar to
diagram.
a phase
It
diagram.
is similar.
Yes, but completely different.
Wait, what?
You're answering a different
A
question.
phase diagram is, I don't actually have a picture of a phase diagram here, but it has different compositions of carbon to iron in it, carbon being on one side, iron being the other. As you add the ratios together, the melting point decreases and then increases again. But this is you take one single point on that diagram, and then you take it to this and watch it as it transforms over time. So this is only one composition of carbon and iron. But at this temperature here, that's the critical temperature, forging temperature, austenite point, whatever you want to call it. At that point, 723 degrees for this alloy mixture anyway, the material becomes fully austenite and it's stable there. If you keep it at that temperature, it will happily sit there forever. As soon as it goes below that, it will start transforming over time. This is a time axis and that is temperature. As time progresses, eventually it will get into this region, which is a mixture of austenite, the unstable stuff, and perlite or bainite, depending on where it is. If it gets all the way at like midway point, 50% of the material's changed, and by the time it gets there, it's 100% whatever's on the other side. And so like this is the equivalent of it being quenched all the way down in cold water. It makes pure martensite, goes all the way down before it can be made into anything else.
So that means it would be quite brittle.
Yes.
So in all of those things in blacksmith, like portrayals of blacksmithing on TV, where they make swords and then they plunge them into cold water, wouldn't that be not?
But that's
accurate?
where tempering comes in next. So what they're doing there is they're hardening the entire blade, and then they temper the center or the back of the blade so it becomes softer while the hard edge of the blade remains intact.
So what is done then to allow that change in structure for tempering?
Tempering. Basically, what happens if you increase the temperature up to here and sit it. It doesn't change the structure. What it does though is it lowers internal stresses, because in the crystalline structure of metals you can have interstitials and superstitials. Basically these means gaps where there aren't any elements, and then elements where they're not supposed to be, and this causes an area of strain, which is increases hardness and brittleness, and basically increasing strain increases brittleness and hardness and whatnot. That's all of these things do. And now when you heat it up, it allows the atoms to rearrange into a more energetically favourable position where they don't have all those gaps, and it becomes softer and whatnot.
On that kind of vague note, what are some of your pet peeves about inaccuracies between the way blacksmithing is portrayed?
Oh god, this is gonna be good.
It's actually not that bad, really. I don't know. What are some commonly portrayed blacksmith things? I can't really think of any at the top of my head.
Getting a horseshoe, heating it up, hammering it, then dropping it in water immediately.
That's actually not that bad.
I guess they all have huge giant muscles, which I guess is
Yeah, no, that's one thing. Well, sure, if you've been blacksmithing for your entire life, you're going to have large upper body strength. But I don't, and I'm a decent blacksmith. It's more about precision than anything else. It's not hard to get into, really. Like, after a few lessons, you can be, well, not good, but you can blacksmith after just a few lessons. It's not that difficult to get into.
Ned Kelly could.
Yes, but in those days they had a lot more blacksmiths and experience in the field than we do today. A common thing I make is arrows, though. Arrow heads. They're really easy to make and fun.
Do those run into mild legal issues? Because I know that there's a long list of assorted banned medieval weaponry floating somewhere.
Not when
Headed at the top of that list from memory are shurikens and nunchucks.
Not when you're in a medieval society.
Obvious exception.
You're even allowed to have the things with the stick and the chain and the ball of spikes.
No, that's one thing that's not going to ever be allowed.
That'd be too much fun.
Yeah.
And similar
That's a good
weapon-related
case.
thing, I saw a great documentary where they made some bronze swords. And this was actually, it was an ancient Britain series, and they'd actually found the locations where copper and tin are sort of exposed on the surface, and pretty much ancient people could just scrape them up. So what's the main? It seemed there was a big difference in making the bronze material. I don't think they couldn't beat it or something, or they had to pour it into
The
a
bronze
shape.
has a much lower melting temperature,
Right.
which means you can use something called casting. And this was something I was meant to mention, and I should mention it now about China again. It's time to talk about them. But casting is a far more favourable method than forging because it's far easier to just pour liquid into a mould.
Right.
And that can make a sword and whatnot. Now, China was working with cast iron for thousands of years before anyone else even knew it existed. And now, the glorious thing about cast iron is its high carbon content can easily be lowered by heating it up in air for a couple of days. And if you finally control that, you can easily make steel. This meant that the Indian nations and China had access to extremely high quality alloys of steel very early on. Such names of these steels are called Wootz steel and whatnot, that most people have commonly heard of, that were famed for the quality of weapons created because they were amazing, basically modern steel.
Is that similar to what Damascus steel is?
Yeah, actually, Damascus steel is an improvement on the Wootz steel method that was introduced into Arabia. They've basically just fine-tuned it. What they do is they get a crucible of cast iron, heat it up, and then keep it hot and let the oxygen burn away, or oxygen burn away at the carbon. Now, there also is an opposite process where a wrought iron is kept in a very carbon-rich environment, and it absorbs carbon and turns into steel, and that's called the assessment process, I do believe, and it's a more modern thing though. But like highly advanced steels were even being used by the Romans and whatnot, and just not in great quantities, and it was extremely expensive. Okay. Yeah, and China skipped 2,000 years of history. And
Alright, any other questions?
well done.